All right, recording is rolling. It is Monday, December 5th. So we're gonna do some stuff on center mass. I have a Kahoot lined up for you guys. You guys saw that. I also have a center mass activity for you guys. Before we all do that, let's do a review on rotational kinematic motion. So I have this turntable, give this thing a spin, and it slows to a stop. Because there's a little bit of friction, a little bit of frictional force, therefore frictional torque. It's going to slow this up. Right. So suppose the numbers attached to that were it was initially spinning at 20 radians per second, and then it slows to a stop in 5 seconds. So there are two questions you can answer from that. What was the rate that it was slowing down, called angular acceleration, which would be a negative value because it was slowing down. Okay. And also, like, how far did it rotate? I could call that angular displacement. Quantify that in radians. Okay. Here, I'll go ahead and walk you guys through this. You guys remember these kinematic formulas? Okay. So if you know how fast it started spinning, that's initial angular velocity. That's this guy, right? Okay. And if it slows to a stop, isn't that final angular velocity is equal to 0? No, true. So you know these two. You also know how many seconds. It took 5 seconds. Okay. So I can solve for alpha angular acceleration. That's the rate that it was slowing down. Okay. So let's try that out. So it's going to 0 radians per second, just playing off this kinematic formula right here, from 20 radians per second. It was slowing down at some rate that we're solving for, and it did this all in 5 seconds. So, okay, can I subtract over 20 radians per second? Call it negative 20 radians per second is equal to 5 times alpha. This is well, 5 seconds, right? Divide over 5 seconds, and get alpha is equal to that negative 4 radians per second squared. It'll be like that, right? Okay, so that's the rate that that turntable is slowing down for all these numbers to play out just like that. Okay. All right, so the follow-up question is, how far did that turntable turn during that interval? How far did it turn? Okay. Guys, what variable on this page represents how far the turntable turned? Isn't that theta that you can measure in radians? I mean, you can also measure in degrees. We've been using theta in degrees for a long time, like going back to the very beginning of this class. Right? But with these formulas, it's always going to be radians, right? And I see it there, and I see it there. So you guys got an option. Right? You could either use this one or this one, right? Or you could even do a graph, right? I'll show you guys all three. How about that? So you go theta equals omega naught t plus 1/2 alpha t squared. I'll just do this one on the calculator screen because we're just going to feed numbers in here, right? Here's 20 radians per second. That was the initial rotation rate. Let's go 20 times, there was a 5 second interval, plus 1/2 times alpha, which we just found. That's right there. Negative 4 radians per second squared times, and then we got 5 seconds again being squared. Okay. Yeah. Okay. Let me pause this right here. Pause. So see, we just punched in these numbers. Having solved for alpha, but we were given all these other ones. I'm looking at theta is equal to, now the number on my screen says 50. And guys, what's the unit for that? Because that's 50 what? Radians, yeah. Right. Because that's how far the turntable's turned. And I said you could also use this bottom formula. Okay. You know what? Actually, let's do this one backwards. Because guys, if it slows to a stop, what is omega final? 0, right? 0 radians per second. Let's see if this actually zeroes out according to this last formula, because we know all these values, right? We were told it starts spinning at 20 radians per second. So I'll go 20 radians per second, square that. I mean, it's in radians per second, so we should be good by this formula, right? Plus 2 times negative 4, which we saw for negative 4 radians per second squared, right? Times, okay, now the answer should be 50 radians, and then it should have turned. So I'll type in 50. Okay. Now, if this really truly works, this should be 0, right? Even if you take square root of 0, it's still 0. Let's see if this is actually 0. It is 0. Ah, right. So third formula checks out. Okay. And you could also have used a graph. Okay. So let's set up some axes for you guys, and I wonder how many guys are going to get this. Omega in radians per second as a function of time, taking in seconds. Okay. Remember, I told you guys the initial omega is equal to 20 radians per second. That's how fast it was spinning to start with. Omega final is 0 radians per second. The time interval was 5 seconds, and that all worked out to be consistent with alpha is -4 radians per second squared. Okay. So can you guys take this information and plot it onto these axes? Can you guys draw that graph? Draw that graph. Can you guys do that? Aha. All right. Think Ian got it. Were you guys also thinking this right here? Right, just like that. Okay. Where it starts at 20 radians per second, and it goes to 0 radians per second, and this happens in 5 seconds, right? Just like that. Okay. Guys, what property of this graph tells you how far it's turned in radians? Well, if the vertical axis is radians per second and the horizontal axis is seconds, what do you have to do to radians per second in seconds to get back to radians? You have to multiply them, right? Because wouldn't that cancel out the seconds? Leave you with radians, right? Which tells you it has something to do with the area under the curve, which in this case is like a triangle shape, right? So it slows down uniformly, right? So can you guys find what is the area of that triangle? Is that 1/2 base height? 1/2 times the base of 5 seconds times the height of 20 radians per second. See, 5 times 20 is 100 divided by 2. Oh, that's 50 radians, exactly what we got before using the formulas and the equations. There we go. So there's 3 different ways to say that a turntable's turn 50 radians. Okay? We did it this way, we check it with this one, and we also did a graph and area under the curve. There you go. 3 different ways to do it. Okay. It's good. Kinematic motion review right there. Okay. All right. Next thing. Let's do a little bit of center mass stuff. You guys have a foam board at your desk? We're just gonna do a fast version of this. All right. So you should have like some weird shaped foam board. The one I have here is like a T shape, and I have a multiple choice. One of these points represents the center of mass. I'll show you guys 3 different ways to find the center of mass. One way is it's whatever point it's going to balance on your finger. So if I turn this upside down and just naturally balance it on my finger, say like I couldn't balance it here, there's a torque. Right. But at some point, I can balance it. Looks like right here, it's balanced on one point. If I flip this over, get out of space. So my finger's pointing right to the letter D. Right. So that's the point here. Right. You guys can try that on yours. Everybody's got a unique foam board. Right. Another way you can get center mass is I have a string with a couple of binder clips. Right. One I'm actually going to clip somewhere on the edge. It could be anywhere around the perimeter of this thing. And the other one I'm going to let be a weight, and it's just going to hang down. Okay. Now, if I hold this from here, this string will always cross straight through the center mass if I hang it vertically. Okay. So, I mean, it's hard to capture that on camera there, but I'll pull this off screen and show you guys that that'll be the case. Okay. Oh, look at that. String's going right through the point D. Okay. Now, does it matter that I clipped it right here? No, I could pick any point. So let me clip it right here and see if it still works. Oh, still works. Okay, there you go. Let me pin that down right there and just put this right in front of the camera. Okay. So even when I clipped it right there, it still went through 20. Right? And the third way that you can find center of mass with the swim board, this one's a little bit tricky. I don't know if it's super practical, but if I take this thing and just threw it in the air and it started like spiraling around, right, there would be one point on this foam board that would actually follow a perfect parabola, follow all those projectile equations that we did way back in the day. And that would be the center of mass of this whole thing, right? As every other point was like wheeling around. Okay, so there you go. So you guys have an opportunity to do that at your desk. All right, now we're about to do this Kahoot. But going into that, I still need to tell you guys about different kinds of equilibrium. Let's look at unstable, stable, and neutral. Okay. What would make something stable or unstable? Okay. So this is what makes something unstable is if any motion would cause its center of mass to move downward, right? Like you guys know, water wants to flow downhill, right? Things to fall wants to roll downhill, right? Things to wind up. So like if I take this triangle, dunk it upside down, even though its center mass is right above this point, right? I mean, okay. If you give it any tip at all, like give it a tiny tip here, point, or just like blow on it with a tiny amount of air, then its center mass is going to want to pivot around that point, which means it's going to want to like go down to the left or to the right. All right, it's going to move downward, right? Which it would like to do. So it's going to be unstable. So we'll do that. Versus, okay, this is the floor down here. Versus, okay, if I dunk that upside down, like this. Now that would be stable. Okay. Now that would be stable because say like I push on the top corner here and starts rotating about this point, for example, okay, that would cause its center mass to have to move upward, have to pivot around that point. Okay. Or if I treat this as my pivot point and I push it from this side, okay, you have to like pivot up like this. Okay, so either way, okay, it's the lowest point it could be right now. Okay. And then how about neutral? Right. An example of that might be like a baseball sitting on the floor. Here's its center mass, and if you give it a push, it'll roll along the floor. Its center mass won't actually get any closer to the floor or further away. So it's like either one of these, but like that neutral stability. Okay. Hey, have you guys ever tried this experiment where you put your back, put the heels of your feet back up against the wall? Okay, and try to lean over and touch your toes? It's not a very good drawing, but you guys can do it, right? Have you guys ever tried to do that? Here, show your demos for you right here on camera. So put my back against the wall, put my heels against the wall, reach down, try to touch my toes. Right? It's really hard to do. Now, some people can do it. But the idea is like your center mass has to stay above this area of support. Right? The area of support is just like going from the heels to your toes of your shoes, right? That's the area of support right here. Plus A for area of support. Once your center mass leaves, like the toes of your shoes, like goes out here, well, now you're unstable. Right? So you're gonna like fall over. So this would be like an unstable situation. Okay. You guys ready for Kahoot? Kahoot. All right, so put my screen over here. All right. Kahoot has something new going on with this. All right. We got Harry. Harry's playing. Oh yeah. What was it? So something like treasure trove or something? So I've never tried this before. So this will be an experiment. This will be new. Gotta find out what treasure trove is. All right, we got Harry, Darcy, and Leah. Let's see. Answer 3 questions correctly to collect treasure for your trove. Okay. Oh, looks like they're giving us a tutorial, right? To collect, quickly tap the treasure as it flies by. Ooh, exciting. Make sure to collect only the jewels. Oh, all right. Oh, is this just on your screens? All right, well, I'll have to record this later then. All right. Yeah, thanks. All right, so with the bronze, you got Leia. With the silver, Darcy. And the gold, Harry. Oh yeah. So did you guys do all 20 conceptual questions, or? Yeah, probably. All right. Well, here, let's do it more traditionally just for the recording here. I can go over these. So. All right. That. Oops. All right. The computer's being a little laggy. But... All right. Let's go classic. All right. And start this thing. Login. I think we need at least one player. Oh yeah.
Is there a worksheet for this?
Oh yeah, there is too. Let me get that for you guys. All right. Let me pause this here. Here, we'll do this one first. Right. Center of gravity of a softball bat. Well, it's kind of a long shoe. I actually got a bat sort of up there on that poster. So would it be in the more massive part of the bat, more massive part of the bat? So I'm thinking. All right. Yeah. Let me get. All right. So. Wrench is sliding over a frictionless tabletop. Right now, different parts of the wrench might follow all different wonky patterns, but the center of mass, you think the center of mass is going to follow probably a straight line path with a regular. Wait a minute. Yeah, regular straight line path. That's what I'm thinking. Regular straight line path. Center of gravity can be located by. Ooh, I just gave you guys a few different methods. Said if you hang it from a string, right? The string will hang through the center of mass. You can balance it on your finger, right? You can also throw it through the air, and the center of mass will actually topple about. But looks like both of the above in this case. Okay. Which following is the center of gravity, a point where there is no mass. Ooh, I like a donut, right? There's a big old hole right there where the center mass would be, right? Like this one's solid. The center mass would be where the milk is. Apple is where the apple core is. Okay? But yeah, a donut. The center mass would be right in the middle of that donut hole. Right. If you hang it from a string, all the strings hang through the center. Object will fall over if the center of gravity is. Ooh, how about? Remember I was saying if you put your heels against the wall and try to reach down, touch your toes. Okay. Once your center mass leaves your area of support, which is just the bottom of your shoes, you're going to topple over. So it's outside the base of support. You carry a heavy load with one arm. Why do you hold your free arm away from your body? They'll probably balance out your torque, right? Let's see. Change the center of gravity of your body, right? Okay, yeah, cool. I guess that's another perspective, right? You move your center of gravity back over the middle of your feet because you have something really heavy on one side. If an object is in unstable equilibrium, any displacement will, I should lower its center of gravity. That's why I just showed you guys a few minutes back. Okay. given any tip, it's going to fall over. It's going to lower its center of gravity. Stable equilibrium. Well, if it's stable, any kind of motion would have to raise its center of gravity, which it wouldn't want to do. That would make it stable. Neutral equilibrium. Yeah, that could be like a baseball sitting on the floor. So any kind of motion is going to center of gravity is just going to stay the same. Right? It's not going to move up or down. If you try to touch your toes staying against the wall, you will probably fall over because your center of mass would go outside your base of support. Center of gravity is what? It's not located above your support. Are those both right? Okay, center of gravity is not located above your support area. Center of gravity is outside your support area. Maybe the yellow one is that? Outside your support area. All right, well, all right. I don't know. I would take it either one, I guess. You go fix that one. The center of mass of the solar system. Okay. Now I know we've usually been assuming sort of it's at the center of the sun, but it's not exactly true, right? As the planets move around, it shifts a little bit. Actually, the center mass of the solar system is what's called the very center, which is pretty close to the center of the sun, but it's not exactly. So I'm thinking blue is actually a better answer. It's called the very center. Right? And the sun also revolves around the very center, but it's not very much motion because the sun's like so massive. The long, heavy tail of a spider monkey enables the monkey to easily vary its. I'm thinking center of gravity. Right. Moves its tail around, center of gravity can move, but none of those other things. Right? You can't change its weight, you can't change its mass. Object thrown into the air with a spin rotates about its. I'm going to say center of mass, center of gravity. Right? That's the other way. I told you guys you can find center of mass, center of gravity. Right? Throw it in the air, it's going to rotate about that point. Got Harry on fire. A plumb line is dropped from a suspension point of a rectangular sheet of plywood. Say half the mass of the wood will be on either side of the line. The line will pass through the center of gravity of the wood. Half the weight will be on either side. I'm thinking the line will pass through the center of gravity. Now, that doesn't mean that the mass is exactly half and half because that's like a torque scenario, right? You can have more mass just like further out, or actually more mass closer, less mass further out would balance the torque, but it should pass through the center of gravity, the center of mass. Okay? A ball resting on the floor. That should be neutral equilibrium. Right? Neutral equilibrium. That's the example I gave you guys. Give it a tap, it'll roll, but center mass doesn't actually move up or down. Neutral equilibrium. A picture hangs on a wall from a wire. It's stable because, let's see, after any small push, it returns to its original position. That's true, right? Its center of gravity is located beneath the supporting nail. That also sounds true. Any slight push would raise its center of gravity. Right, this sounds true also. Okay, so I'm going to go with the green one. I think these are all true statements. I'm going to draw that one out for you guys too. Right, so switch the screen over here. All right, so we're thinking like stable equilibrium for a picture frame, right? So I got a picture frame. And here's the supporting nail. Here's the wire. Right? Here's the center mass of the entire picture frame. Right? Center mass is right here. Okay? So say give this a push, it's gonna like rotate about this pivot point. Okay, which is gonna be like this. And if I give it a push this way, so rotate like this. Okay. So it looks like its center mass is already at the bottom of the valley. So it's already stable how it wants to go. Right. If you push out from that, it's just gonna go back to where it was. Right? Submerge a ping pong ball in a glass of water. The center of gravity of the glass of water. Ooh. Huh. It's a tricky one, right? I'm thinking all the water would have to rise, like the water level would rise, right? Because something that's not very massive, filled with air, is being pushed down. So I'm thinking the answer is going to be it rises, right? And then if you let go of the ping pong ball, wouldn't the ping pong ball shoot up and then all the water around it would settle down? Okay. Which is, things naturally want to do that, right? Water wants to flow downhill, things want to roll downhill. Okay. So I'm thinking if you push the ping pong ball into the glass of water, the center mass is going to rise. And then if you let the ping pong ball go, everything reverses and the center mass in the water falls. So maybe with the blue one. Yeah, there you go. The sun has several planets orbiting it. It actually wobbles as it moves through space. Yeah, that's what I was talking about with the barycenter, right? Because the sun actually revolves around the barycenter, but the sun is like 99% of the mass of the solar system. So usually you say, okay, wow, everything's sort of orbiting the sun. But yeah, I'm thinking it's actually going to wobble about its barycenter as it's going around the Milky Way, right? Our whole solar system is moving through the Milky Way. Milky Way has like spiral arms and for a baseball bat thrown in the air, the center of gravity follows a smooth parabolic path. Yeah, that would be the only path on the baseball bat that follows the smooth parabolic path, right? It's just the center of gravity. Okay, all the other parts are following weird like spiral shapes, but yeah, center of gravity of the bat. Do that. All right, last question. The center mass of an object is always located at the object's geometric center. Well, what if you had an object that was made of half steel and half foam? Like its geometric center might be somewhere, but if its center mass is a lot closer to the steel side, right? So I'm thinking this is going to be false, right? Because you might have different materials, different densities, right? Maybe distributed differently at different locations. There you go. All right. Getting the gold. So that is taking us to the end of class right there. All right. And then tomorrow I'll do a rotational inertia lab with you guys.